Okay, can you see my desktop?
Yes, perfect.
Okay, I want to introduce in this workshop some of the works that we are carrying out with my research group, and in particular our architecture for future generation IoT environments that are cognitive enabled and edge computing based, and sorry. Okay, so I am Andrea Vinci. I'm a researcher at the National Research Council of Italy, and I am a part of the Edge Intelligence group and our research covers topics like Internet of Things, cyber physical systems, edge computing, artificial intelligence, autonomous control systems, and aggregated computing. In this talk, I want to introduce what we intend when we speak about a smart cyber-physical environment and some past experience in developing smart environments and the design of our Cogito architecture. Then from the Cogito architecture, I'll present a simple application which exemplify what we think is cognitive smart environment needs to be, sorry. So a smart cyber physical environment or a smart environment is a physical environment enriched with sensing, actuation, communication, and computational capabilities, aiming at acquiring, exploiting knowledge about the environment so as to adapt to its inhabitants' preference and requirements. So if we think about a building, for example, we need a large set of devices that gathers information about the environment status, and from this information we can profile users and try to make the environment more comfortable for the users itself. So the design and implementation of significant smart environments is a challenging and a complex task because there are many issues that to be taken into account when developing such environment. They are highly dynamic, naturally distributed. I made an example for a building, but we can think also about a street or a city. They gather and have to put together heterogeneous technologies, devices, and protocol, and a different number of hardware and software components. Also, the ever-increasing complexity of the offered services leads to the exploitation of cognitive-based technology, aiming at realizing systems able to automatically adapt to changes, users' behavior, and anticipating and predicting their activities. In order to deal with the foregoing aspects, the use of well-suited architectures, platform, and methodological approaches become of utmost importance, as architectures promote modularity and separation of concerns, offering basic abstraction entities which can be exploited to handle complexity and reduce the effort during the design phase. Methodological approaches promote a more structured design phase and permit to exploit the different competence of the team involved in the design of smart environment. And the platform permits the development of application which exploits ready-to-use solution and services tailored for the exploitation of a specific architecture and methodological approach. with our group have developed a framework that is called eSapiens, which is Java distributed middleware Java-based and agent-based. And with this in mind, we deployed and developed some application in the past years that spans from smart city application prototype, like the smart street, which is a distributed edge nodes application, which try to both monitor the status of the street in terms of temperature, humidity, and issues like pollutions, pollutant concentration, and also try to detect anomalies in a distributed fashion or detect frequent pattern of exploitation of the street. Another kind of distributed application based on the iSapiens framework was the smart urban drainage network, which is a decentralized IoT application for optimizing the behavior of the urban drainage network simulated in the city of Cosenza. This is a distributed and decentralized application made of agents that can sense and control the status of the conduits in the network, and can close and open a set of gates in order to avoid, for example, flooding phenomena during intense rains. So from this application, we learned something. In particular, that our made platform highly simplified the development of such application, because it permits, simplified the management of heterogeneous hardware devices, spanning from sensor to more complex gates. It simplifies the management of the heterogeneous communication protocols, as we used protocols in the same application, which spans from ZigBee to Wi-Fi and so on. And iSapiens also permits the distributed computational the exploitation of distributed computational resources that are scattered at the edge of the network and in the cloud. Also, the agent metaphor naturally permitted to design and implement dynamic systems where location-independent functionalities can be offered to the final users. But our platform lacks of something, and in particular, from the use, from the development of application, it emerges that some frequent tasks are completely application dependent, but some facilities could be provided in a future platform. And in particular, for example, the aggregation and the filtering of data coming from data sources can be provided as a new layer of our platform. The implementation of complex agents behavior, cognitive behaviors, which learns and adapts from the system for controlling the system, and the management and the optimization of the resource available is also a common issue. So we are developing a platform that is named as Cogito, an architecture that is named as Cogito, which is presented in this picture. In particular, the Cogito architecture is based on, is deployed on a set of nodes which span between the very edge of the network and the cloud. Each node contains the components that are depicted in the right part of the figure, and in particular, so it is like a distributed middleware, and in particular, the most important, the behavioral part of application written for this architecture consists of a set of application agents that live in a multi-agent container, a distributed multi-agent container. So the agents the agents work together and interacts to furnish some services to the users, some high-level services to the users, like load scheduling, evacuation, thermal comfort, predictive maintenance. On support of the agent behaviors, there are a set of modules that are furnished from the architecture. In particular, the virtual object container is a component that abstracts physical devices in order to hide to the top level, the agent one, the complexity which is due to the heterogeneity of protocol and physical objects in a system, and so furnishing the same API to the agent layer. Also, considering the data aggregation and filtering, we introduce a region module where this region permits to compute aggregation and filter on considering a region abstraction of which is a view of the data produced by both the devices and eventually by the agents. This region can be an aggregation of a certain kind of measurements or information, or even a class, computing a clusters of interesting data and information in a decentralized and distributed fashion. Another important component is the one called cognitive API that furnishes to the agent layer a set of an integration of a set of software and computation library which for computing artificial intelligence or machine learning tasks. Finally, the management module management modules are devoted to manage the resources and identify which is the best node for deploying and executing a specific agent or machine learning task. So with this architecture in mind and compliant with this architecture, I want to show a simple application for the comfort management in a room, which leverages deep reinforcement learning and considers the human in the loop. In particular, this application has the goal of manage the thermal comfort in a smart building, and consists of a cognitive system that adapts its behavior for preventing user interaction. Our assumption is that a user interacts with the system when he or she experiences discomfort. So maybe if a person turn on his fan coil is because it's cold or hot in his environment, so it's uncomfortable. And so our system tries to minimize user interaction for reaching the comfort of the inhabitants of an environment. This is our approach. The focus is on a deep reinforcement learning based controller, which gather information about environmental parameters as temperature, humidity, and so on, presence and activities of the people in the room, and energy consumption of appliances, and also takes into account the user interaction of the users with the environment itself. The controller tries to maximize the human reward and an environmental reward when acting on the HVAC system or other objects that may be actuable, like doors, windows, and so on. The approach foresees that an environment can be a simulated one, so the deep reinforcement learning controller can be pre-trained in a simulated environment and then deployed on a real one. As an experimental case study, we can consider, for example, a room and the temperature comfort in a room. And in particular, the state that is available to the deep reinforcement learning controller consists of 4 quantities, which are the indoor temperature of the room, the outdoor temperature, the fan coil temperature, and the fan coil state, which is if it is on or off. The actions that the controller can make is the switching of the fan coil from on or off, or from off or to on. The deep reinforcement learning controller, as I said, gets its reward both from an environmental component, which is related to the administration of the building, so the set point of the centralized HVAC systems, and a human reward that is tailored on the interaction of the people with the system. And in particular, it is fundamentally a penalty for each interaction between the user and the HVAC system. For simulation purpose, we used a thermal model based on Newton law. So the current temperature depends on the current temperature in a room depends on the temperature in the room at previous steps, and from the temperature of the outdoor environment and the temperature of the fan coil if it is on. The people behavior is modeled in a probabilistic fashion through a sigmoid, and in particular, the probability is for a people to interact with the system, so to manually turn on or off the fan coil. And this depends on the delta T max parameter, which is in some way a tolerance degree. So the higher is delta T max, and the less the higher the moderate person will tolerate differences between its comfort temperature and the current indoor temperature. The reward considers both the human and environmental components, and in particular is a weighted sum of both of them, where the environmental reward is the difference between an environmental set point, which in this case is of 20 degrees, while the human reward is a penalty given when the person interacts with the system, as I said before. Just some results related to this approach. We have considered 2 kinds of people to validate the approach, which is a very tolerant user, having delta T max modeled with delta T max of 16, and a very intolerant user modeled to a delta T max of 2. So on the top side of the slide, you can see how the deep reinforcement learning controller learn how to manage the system, and in particular with having as a control as a scenario given by even when the system is shut off, so only people can interact with the Franco system, is the purple line, and this is the temperature for each simulation days. And in particular, we have that our system, when considering the combined reward, so the red line, learn how to manage the HVAC system to guarantee a temperature between the environmental setup and the comfort of the person we modeled. On the bottom part, we have the count per day of the interaction made by the user with the fan coil. And in particular, it is interesting that for an intolerant user, the system is able to make less and less the interaction between the user and the fan coil system, as it learns how to prevent the user behavior, okay? And so reaching the comfort level without the interaction of the users. This approach will be deployed in a real environment. This is a picture of the smart laboratory that we have at our institute, and which have many devices deployed both for monitoring and controlling purposes, and is our test bed for this and future application. In particular, given the aforementioned approach, we can try what happens if we consider a multi-user environment, for example, and also try to optimize the behavior in terms of power efficiency and comfort, lighting for comfort, and correlation between lighting and thermal comfort. For example, if you open the curtain in summer, you can expect the temperature will grow in the room. So I finish for now, and you are cordially invited to submit to the special issue Emerging Internet of Things Solution and Technology of Electronics Journal, as I think it matches with the NEGICS workshop. So thank you. And
thank you.
Thank you, Monica.
While I'm waiting, if there are any questions from the audience, I would like to ask you a question about the last thing you were actually presenting. So if I understood properly, you were saying that you are trying to, in some way, learn from how the human in the loop behaves, so how it interacts, and the interaction of the human is actually a feedback that you give to your system. Yeah. That says that something has to be improved. My question is the system, so you can have the same system in different environments, and then you learn different things according also to the customer, because different customers might have different preferences. So you are learning for specific users, right?
Okay, yes. So our system tries to learn from the user that live in the environment. Okay, And
okay.
So it can be pre-trained on a generic user, but when deployed, it continues to learn and adapt to the user that lives in the environment. Also, if, for example, a room changes the users, you think to at an office where some people enters in the office or the desk is occupied by other people, the system will learn and adapt to the new people on time. Okay. FutureWorks aims to profile single people and choose the best reward between choose the best behavior to be a compromise between the different users' preferences. Okay.
Okay. Thank you.
Thank you.
So now I would like to switch to the next talk. That is Hernan is the speaker.
I am here.